Good morning. Today, I'd like to start talking about our next major topic, which is how to make our bag of tricks for integrals bigger. To get started, I want to review everything we're supposed to already know about how to do integrals from the first semester. We're going to have a list of 20 formulas that we can use. In each of these formulas, the letter U is used for the variable name. The K in the first equation is a constant. This says that the integral of a constant times some function is the constant times the integral of the function. We will see examples of all of these things shortly. If I need to add or subtract two functions and then find an integral, I am allowed to do the two integrals separately and then add or subtract them as appropriate. The integral of the constant function 1 with respect to u, which some people would write as the integral du, thinking of this as being 1 times du. This integral is the variable plus the constant of integration c. In this equation, the n is supposed to be a constant number. It doesn't depend on the variable. And this formula will always work except when n is equal to -1. Antiderivative of the variable to a constant power with respect to the variable is you increase the power by 1, and then you have a factor that is the reciprocal of the new power. In the case where n is -1, the integral of u to the -1 would just be the integral of 1 over u, which in the first semester we said was the natural log of the absolute value of the variable plus a constant. Some people, again thinking of this as multiplication, would write it in this form. We already have enough information here to allow us to integrate any polynomial. Ordinarily, we don't write in all of the details, but I want to do that in this case for emphasis. The name of the variable in this problem is literally x. I'd like to find an antiderivative of 5x squared plus 6x plus 2. Because of the sum and difference formula, I can write this integral as this integral plus that integral plus that integral. Because of the constant times function rule, I can write this integral as 5 times the integral of x squared with respect to x, this one as 6 times integral of x to the 1 power with respect to x, plus 2 times the integral of 1 dx. Each one of these things is on the list of formulas that we talked about on the previous page. An antiderivative for x squared with respect to x is 1/3 x cubed. An antiderivative for x with respect to x is 1/2 x squared. There's the 1/2. An antiderivative of 1 with respect to x is x, 2 times that. And then we traditionally wait till the very end to put the constant of integration on. Ordinarily, we don't put this much detail in, but I may ask you to do this in order to emphasize what's going on. As an example of why we use the alternative letter u in all of our formulas, imagine that you wanted to do an integral where you had a product of an exponential function with a polynomial. The thing that's being fed through the exponential function, though, isn't just x. It's x squared plus 4x plus 2. But then, fortunately, you have a factor of 2x plus 4 in the integral also. An observant person will notice that the derivative of x squared plus 4x plus 2 is 2x plus 4. So obviously, in the language from Calculus 1, I'd want to do a u substitution here. When I write up something like this, initially I can be as messy and as confused looking as I like, but when I go to hand something in, I'll want to write it up very neatly, like this. Let u equals x squared plus 4x plus 2. The derivative of u with respect to x is 2x plus 4. du is 2x plus 4 dx. Notice that those parentheses really are necessary if you want to think of this as kind of, sort of multiplication. In the integral, you have 2x plus 4 dx, which is exactly du. So when I write this bit down, I'm just going to write du all by itself. The rest of my integral is e raised to a certain power, e raised to the u power to be exact. The integral is the integral of e to the u du, which is on our list of formulas. This is e to the u plus a constant of integration. Then I recall that u is x squared plus 4x plus 2 to obtain my answer. Sometimes, instead of doing a u substitution, a little bit of algebra is called for. If I needed to integrate the fraction x squared plus 2x plus 3 divided by x with respect to x, I can do some algebra that will help me out here. I do have to warn you, this is not the same as the integral of x squared plus 2x plus 3 divided by the integral of x. Integrals don't act that way. On the other hand, I do know how to add fractions together. X squared plus 2x plus 3 over x is the same as x squared over x plus 2x over x plus 3 over x. That is to say, the thing that I'm integrating is the same as x plus 2 plus 3 divided by x, and all three of those things separately, which are added together here, are things that I know how to integrate. You have to be very careful not to give in to the tendency to make up algebra rules that will help you out. We actually have to follow all the regular rules of algebra, and we have a very small set of rules about integrals that we can follow as well. Let's look at another one of these. I have no general rule to help me out here, but if I'm sneaky enough, I'll make an observation. The bottom of the fraction is a linear polynomial. It's a constant times x plus another constant. The second constant is twice as big as the first one was. If the upstairs function, which is also linear, was also a constant times x plus twice that constant, I could do some canceling out. Unfortunately, that isn't what I've got here. If I could do what I'm thinking of doing, I would much rather have an x plus 2 upstairs instead of an x plus 1. I can do a little bit of algebra trickery to make that happen at the expense of having to do a little bit of extra work. So I wish it said x plus 2 upstairs. So I'll write it as x plus 2, which is not right because it's no longer equal to x plus 1. I'll balance the books by subtracting 1 back off upstairs. This is still x plus 1 upstairs. I've just got it written in a rather strange format. Here, the reason that I like this so much is the bottom of the fraction is exactly 3 times the top of the fraction. So x plus 2 divided by 3x plus 6 is a constant. It's 1/3. If I can deal with that, I'll be in business. An antiderivative for the constant 1/3 is 1/3 x. And then to get this integral, I'll make a u substitution. I'm very nearly violating my own legibility guidelines, but this remaining integral, since it's a side issue, I decided that I had enough room over here on the side to do it in some sort of reasonably readable manner. The remaining integral works out to be 1/3 natural log absolute 3x plus 6. My 1/3 here looked a little bit too much like a 1/2. After doing this, we add our constant of integration, and we have our result. So sometimes you can take a problem and algebraically mess with it a little bit and turn it into something that's relatively easy to do. Besides these 5 formulas that we've been looking at already, we have an additional 15 of them. Rather than make this review of basic integration rules into some sort of overwhelming ordeal, I believe I'm going to bust it up into several smaller little videos. So I am going to mention, though, these are the first 5 of our formulas, but we do have 15 other ones. We have integration formulas involving exponential functions, the integral of sine, cosine, and tangent. That takes us to 10 of our 20 formulas. In a less familiar way, we know antiderivatives for the cotangent, the secant, the cosecant function. We know antiderivatives for secant squared and cosecant squared. And lastly, we know the integral of secant u tangent u du, cosecant u cotangent u du. If a is a positive constant, we know how to do integrals of 1 over square root of a squared minus u squared, the integral of 1 over a squared plus u squared, and the integral of 1 over u times the square root of u squared minus a squared. In an upcoming video, I will do more examples of these kinds of things. I'll make another one of these small videos pretty soon. In the meantime, I hope everybody has a good day, and I'll talk to you again soon.